Okay, we're going to look at doing some stoichiometry to figure out the theoretical yield of a chemical reaction. In other words, how much product we're going to make. But we're going to be facing this problem with two amounts of reactants, because that's how we're usually going to do it in the lab. We have some of this and some of that. We put them together. One of those reactants is going to run out first. And it's not always easy to figure out which one it's going to be, because we have our reactions balancing differently, like how in this case it takes 4 C's to react with 1 S8 to make 4 CS2s. So it's taking a lot more C's than it is S8s. Molar mass also matters. Since we're measuring things by mass, we might only need 1 S8 for every 4 C's, but if S8 is a massively heavy molecule, then it's going to take more grams just to have the same number of moles of S8 than it would to have the same number of moles of C. So in order to figure out what our theoretical yield is going to be and what our limiting reactant is, which chemical runs out first, all we have to do is figure out the theoretical yield twice using our 100 grams of carbon and our 500 grams of S8, and in both cases trying to figure out how much CS2 we should make. Whatever makes the least amount is what's running out first. So we're kind of pretending like we're doing these independently. Like if I had 100 grams of C, how many grams of CS2 could I make? Okay, or if I had 500 grams of S8, how many grams of CS2 could I make? Okay, so they're going to be two problems that are quite similar in setup. Okay, we're going to end up at the same kind of value. We're still going to end up with grams of CS2, but the amount is going to depend on how much of each of these reactants we start with. So the rest will probably be easiest if we actually see it in action. So let's try it. Let's start with 100 grams of carbon reacting in this reaction to make CS2. So we're going to see how much CS2 we can make out of this reaction. So I'm starting with 100 grams of C. Okay, I would have a stoichiometry diagram and a periodic table handy if you're following along with this. Our first change that needs to happen in order to go from grams of one thing to grams of another, mass of one thing to mass of another, is I have to get rid of my grams of my old chemical. I don't really want to know about carbon. I want to know about CS2. So I need to get out of carbon. First step for that is getting rid of this grams of C. Oops, let's make that a little bigger. Grams of carbon unit that I have that I don't want here. Okay, and the next stop in getting to grams of a different chemical is moles of carbon, moles of my same chemical here. So moles of CF on top here. This is my first change. I'm going from grams of something to moles of something. Moles is like our universal translator for stuff. Okay, now this is not a mole to mole ratio, so I can be 1 with moles here. And then what this fraction bar is asking me is, well, hey, how many grams of carbon are in 1 mole of carbon? That's the molar mass. That's what the periodic table is telling us. So if you go and find carbon on the periodic table, there are 12.01 grams of carbon in 1 mole of carbon. This will allow us to cancel out our grams of carbon units. We should be left with moles of C, which is closer to what we want, but it's not what we want. So we need another fraction bar. So let's set one up. Here. All right, so now the unit I need to get rid of, my old unit, that's going to go on the bottom here, is my moles of C. So as long as I know there's a unit to get rid of, it's going to go on the bottom of my next fraction bar. So it's like I'm already halfway there, moles of C there. All right, so what do I have up on top? Well, that's going to be moles of the new chemical I want to know about. In this case, I want to know about CS2. I want to know about moles of CS2. Now, this is a mole to mole ratio. I have moles on the top and the bottom, so I can't just be 1 with moles here. This fraction bar is asking me what the relationship is between the moles of one chemical and moles of another. If you treat these coefficients up here not as atoms or molecules, but as moles, like 4 moles of C can make 4 moles of CS2, we can literally just steal these numbers and throw them down in here. Okay, so if I had 4 moles of C, I should be able to make 4 moles of CS2. So I'm just stealing these numbers right from the balanced chemical reaction equation to use just for my mole-to-mole ratio, not everywhere where moles is, just the mole-to-mole ratio from one chemical to another. This should help me get rid of my moles of C units. All right, so I've got moles of CS2, but again, I want to figure out the theoretical yield in grams of CS2. So I can't stop here. All right, I need one more fraction bar, where this last unit I need to get rid of is moles of CS2. Moles of CS2. All right. My last conversion is to go from moles of CS2 to grams of CS2. And again, keep that stoichiometry diagram handy if you're still not quite sure, like, well, what can I convert to next? Use that to kind of figure it out. Kind of rely on that. All right. This is not a mole-to-mole ratio, so I can be 1 with moles right there. So this is asking me how many grams of CS2 are in 1 mole of CS2. So I just have to add up 1 C and 2 S's to get the molar mass of CS2. So our carbon is 12.01. I have one of those. And sulfur is 32.07. I have 2 of those. So if I add up 12.01 and 32.07 and 32.07, I should get 76.15 grams of CS2 in 1 mole of CS2. This should help me cancel my last remaining units that I don't want. So if I take 100 grams of carbon and I multiply by everything on the top, divide by everything on the bottom, I should get my answer converted into grams of CS2, how much carbon disulfide I can make starting with 100 grams of carbon. So 100 times 1 divided by 12.01 times 4 divided by 4 times 76.15 divided by 1. And again, you don't really need to include the ones in your calculations, but I like to do it to make sure I didn't miss anything. So I've got 633.22 grams of CS2 that I can make from this reaction. As long as I have 100 grams of C, and I'm assuming I have as much S8 to react with as I can have. So if everything was going my way, and I used 100 grams of carbon, I should be able to make 633.22 grams of CS2. But what if I didn't have enough S8 to react with? That's why we also are going to figure out how much CS2 we can make based on this 500 grams of S8. And we're going to compare those two numbers. So this is one step. This is one possible theoretical yield, but it might not be the theoretical yield. So let's try another one, where this time we're starting with our other reactant, 500 grams of S8. Multiplying by a fraction bar. I'm getting rid of grams of S8 on the bottom first, okay, because that's the unit I have to get rid of. If I'm trying to go from grams of one thing to grams of another, I got a long ways to go. So grams of S8, so I'm getting rid of on there. My next stop is moles of that chemical, just how I went from grams of C to moles of C. So I'm going from grams to moles. Moles of S8. All right, this is not a mole-to-mole ratio, so I can be 1 with moles. So then this is asking me how many grams of S8 are in 1 mole of S8. The molar mass of S8 is 32.07 times 8, because there's 8 sulfurs in here. Okay, that's 256.56. That is a massive molecule. 256 point, I'm going to run out of room here. Scooch this over. 256.56 grams of S8. All right. When I work out the math, this will cancel out my grams of S8 units. Then it is on to the next fraction bar. This one's a mole-to-mole ratio. I'm getting rid of moles of S8. Moles of S8 is my old unit, so it's going on the bottom. My new unit is going to be moles of CS2. Moles of CS2. Okay, so since this is a multimole ratio, I can't be one with moles, but I can just steal the numbers from the balanced chemical reaction equation up here. All right. Chemical reaction equation says if I use 1 mole of S8, I should be able to get 4 moles of CS2. So that's what I'm going to use in my ratio down here. Okay, if I use 1 mole of S8, I should be able to get 4 moles of CS2. And I'm just stealing those numbers right from the balanced chemical reaction equation up there. Okay, so now what's next? Well, this should help me cancel my moles of S8 units there. So now that I'm in moles of CS2, I can get rid of moles of CS2 and finally just get grams of CS2. So I've got moles of CS2 on the bottom. Up on the top, I've got grams of CS2. All right, this is not a multimole ratio, so I'm going to be 1 with moles. And then this is asking me how many grams of CS2 are in 1 mole of CS2. I mean, I already did that. It's right there. So these problems actually kind of lend themselves to like, oh, you actually already did some of this, so you can kind of just reuse it. You'll notice that this kind of chunk, let me outline it here in a color I haven't really used yet, I'll use green. This kind of chunk here is going to be the same because we're solving for the same chemical. The end of our conversion is the same. The only thing that's different is the fact that we're starting with a different chemical. So that kind of helps out. You already have some of the rest of the problem done once you've done the first stoichiometry problem. So you can make use of that if you'd like. Okay, so if you add up a C and 2 S's, or if you just reuse this number you got up there, we have 76.15 grams of CS2 and 1 mole of CS2. Our moles of CS2 should cancel out. All right, so now if I take all this and plug it in, 500 times 1 divided by 256.56 times 4 divided by 1 times 76.15 divided by 1, I get 593.62 grams of CS2. Okay, so if everything went the way I needed to and I had plenty of carbon to react this with, I could use 500 grams of S8 to make 593.62 grams of CS2, which is less than what I could make with my 100 grams of carbon, which is interesting. So even though I'm starting with more grams of S8, I can't make as much CS2 with this. Okay, so if I were to put these two together, one of these is going to run out first, and it's going to be the one that makes a smaller amount of product. By the time I hit 593.62 grams of CS2, I've run out of S8, which means I just have leftover carbon that's not being used for anything. So we call this S8 the limiting reactant because it's going to limit how much product we can make for our theoretical yield. Our carbon is our excess reactant, which means that it's extra. We're going to have some left over afterwards. So this is our excess reactant, and our S8 is our limiting reactant. Okay? I can only use the theoretical yield that comes from the limiting reactant because, again, that's what's going to run out first. I'm going to have extra carbon that's not actually used to make product. So this 100 grams is not all going to get used. Just because I have, 3 bags of chocolate chips in my cabinet doesn't mean I'm going to use all of them when I bake cookies. I'm probably going to use maybe 1 bag at most, unless you really want them chocolatey. So if I want to get the right theoretical yield, I'm going to have to go with the smaller amount. So S8 is my limiting reactant. And the theoretical yield is how much CS2 I can make out of that reaction. So that would be 593.62 grams of CS2. And this other amount doesn't really mean anything because I'll never make that much CS2 as long as I'm held back by this amount of S8. Okay, now based on this theoretical yield, we can use an actual yield of this chemical reaction in the lab to figure out what percentage of what we expected to get we actually got. So our actual yield in this case is given to us instead of us actually doing it in the lab. It's 580 grams of CS2. All right, so that's my actual yield. Theoretically, I should be able to get 593.62 grams of CS2. All right, so if I take my actual divided by my theoretical and multiply by 100, I get a percentage of how much do they actually get compared to what I should have gotten. So I'm going to take, 580.0 grams of CS2 divided by 593.62 grams of CS2 times 100. Okay, and if you have a calculator that has a percent button, be careful. I'm putting this percentage thing here to show like it should come out as a percent, not to use the percentage in your calculation. Okay, otherwise, sometimes it'll take this 100%, and that's basically just multiplying by 1. 100% of something is just 1. So don't multiply by 100%, multiply it by 100 to make it a percent. It's kind of confusing. Okay, so if I take 580 divided by 593.62, multiply by 100, we get a percent yield of 97.71-ish percent of our product yielded. So we got about 97.7% of what we expected to get, which is pretty darn good. The closer to 100% your yield is, the better you are, and the lower your chances that you made a mistake or an error or a mishap happened in the lab. Okay, so this is our general process. We start with two possible amounts of reactants that can be thrown together in a reaction. If there's just one reactant, you just use that one amount of reactant. There's nothing else to kind of limit it besides that one. But as long as you have more than one reactant, we are using these two things to do two different stoichiometry problems to see how much of a product we can make. Usually we just go to whatever theoretical yield we want because then we have that answer ready as long as we find the smallest one. So use stoichiometry to go from grams of each reactant to grams of our product that we care about, in this case CS2. And whatever amount comes out the smallest is our limiting amount. It's our theoretical yield. The other amount doesn't mean much because we'll never be able to react that much to make that much product. The other reactant's going to run out first. So the reactant that gives you the smaller amount of product is called the limiting reactant. It's what cuts off our amount of product early, whereas the other stuff is the excess, and it's just kind of there to make the reaction go and doesn't do much else for us. So the limiting reactant's theoretical yield is what we use for all our following calculations. It's what we would expect to get in the lab. It's what we would use for a percent yield, or if you're doing percent error, which is kind of like percent yield but with a twist, then use it for that too.